Good morning, students. In this lecture, we will study how we can be able to solve systems characterized by constant coefficient differential equation. That means the relation between the input and the output described by differential equation. For example, from k is equal to 0 to n ak, the k is derivative of y, the output, by dtk is equal to from k0 to mbk, the k is derivative of x of t by dtk. This is a differential equation which gives the relation between the input x of t and the output y of t. The output y of t. So that means I have, for example, here my system h of t. H of t is my system. Remember what's h of t? H of t is called the impulse response of the system. I have an input x of t and I have an output y of t. In the previous chapters, in chapter 2, for example, we get the output by convolution. Y of t is equal to x of t convolved by h of t. So it was a little bit complicated, tedious to do the flip, the shift, and so on, as you know. Now in this chapter, instead of x of t and h of t, what if we are given the differential equation? The differential equation which gives the relation between the input x of t and y of t, given by this, okay? Now, as you know, y of t, x of t convolved with h of t, and in frequency domain we have y j omega equals to x j omega times h j omega. Convolution in the time domain will change to multiplication in the frequency domain. So for example, if one of them is given, if two of them is given, you can determine the other variable in frequency domain and you change it to time domain. This is a relation between time domain and the frequency domain. Now let's go to the differential equation. When I write, this is a compact form. When I write it in the long form, when k is equal to 0, I have a0 times y of t, because no derivative for y. And if k is 1, a1, the first derivative of y. If k is 2, plus a2, the second derivative of y, plus continue until what is the last derivative? The last derivative is n. an, the nth derivative of y, or y of t by dtn is equal to, on the right side, what I have, the input. When k0, b0, x of t, plus when k1, b1, the derivative of x of t, when k2, b2, the second derivative of x of t, and plus continue, and last, when k is m, bm, the m's derivative of x of t. So usually n is greater than or equal to m, and we call n is the order of the differential equation. For example, if capital N is 1, we have first order system. If capital N is 2, we have second order system. If capital N is 3, we have third order system, and so on. Now this is time domain. This is time domain, so we solve it, we change this to frequency domain, and we find the relation between the output y and the input x in frequency domain, in frequency domain. Because here, when the time domain is changed to frequency domain, as you see, y j omega is equal to x j omega times h j omega. What is h j omega? H j omega is equal to y j omega divided by x j omega. And we call this the frequency response of the system. So from the relation between y and x in frequency domain, we can find the frequency domain. Now to change the differential equation to frequency domain, we use this relation. If I have the derivative of x of t, this is from the properties of Fourier transform that we studied in the previous lecture. The derivative of x of t is j omega times x j omega. The second derivative of x of t is j omega squared times x j omega. The k's derivative of x of t is j omega power of k times x j omega. For example, if k is 0, it will be the zero derivative. The zero derivative means no derivative, so j omega power of 0 is 1, so it will be x j omega. So by using this, let's change this, the first part, ak, the derivative of y by dtk will become ak j omega power of k times y j omega. And the right side, bk j omega power of k times x j omega. And I have the summation. Remember, I have the summation. So y j omega over x j omega, from this relation, y over x is equal to summation bk j omega power of k over summation of ak j omega power of k. So what is this? Y j omega over x j omega? We know h j omega. So this rational function of as a function of omega gives me the frequency response of the system. Remember, this is again the compact form. So in long form, when we write it, we can expand it. When we expand, this will become b0 plus b1 times j omega plus b2 j omega square plus bm j omega power of m over a0 plus a1 times j omega plus a2 j omega square plus continue plus an j omega power of n. Now, as I said, given x of t and h of t, how we get y of t? Change x of t to x j omega, h of t to h j omega using Fourier transform, and from that we get y j omega, x j omega times h j omega, and we change y j omega to y of t. What about given x of t and yt, how we get h of t? So x of t, the input, and yt is given. Then we change x of t to x j omega. We change yt to y j omega. That means to frequency domain. And we get h j omega is equal to y j omega over x j omega. And then we change the frequency domain to time domain using inverse Fourier transform. Now let's do some examples for systems characterized by differential equation. Okay, now let's take the first example, which is easy. Let's have a first order system dy by dt plus a times yt is equal to x of t, and a is greater than 0, or a is positive number. So this is a differential equation relating the input y, the input x of t and the output y of t by first order differential equation. Now, how we find h of t? Change again to frequency domain, change the equation to frequency domain. The derivative of y of t will become j omega times y j omega. A times y of t will become a times y j omega. X of t will become x j omega. And what is common here? Y j omega. So in bracket, j omega plus a is equal to x j omega. Then y j omega over x j omega is equal to 1 over j omega plus a. What is this? This is the frequency response of the system, h j omega. So we can change this to time domain. When we change to time domain, remember a is a positive real number. So from the examples that we did in the previous videos, if I have 1 over j omega plus a, the inverse Fourier transform of this is e to the power of at times ut. Ut is the unit step function where a is greater than 0. So we can change directly using the previous method, because we already found the Fourier transform of e to the power of at times ut, which is equal to 1 over j omega plus a. Okay, now let's continue. Now we have another system. The second derivative of y plus 4 dy by dt plus 3y of t is equal to the first derivative of x of t plus 2xt. If you see this differential equation, the order of the differential equation is second order because I have two here. A0 is 3, A1 is 4, and A2 is 1, and so on. So what is the problem? The problem is find h of t, or the required is what is h of t. So again, we change to differential equation. The second derivative will become j omega squared times y j omega. The first derivative will become j omega times y j omega, so 4 times this, and 3 times y j omega, and the first derivative will become j omega times x j omega plus 2 times x j omega. Then what's common here? Y j omega. Y j omega squared for j omega plus 3 is equal to what is common here? X j omega plus 2. Then y j omega over x j omega is j omega plus 2, j omega squared plus 4 j omega plus 3, which is equal to h j omega. Now we found already the frequency response given by this. Now what is this in time domain? When we change it to time domain, we have this inverse Fourier transform formula. If we substitute this here and find h of t, it is not easy. It is not easy to do this integration. So what is the easiest way? The easiest way is, we need to change it to partial fraction. We do partial fraction expansion. Partial fraction expansion of the frequency response, h j omega plus 2 or j omega square for j omega plus 3. If we say, for example, j omega is s, the denominator is like s square plus 4s plus 3. And if you see this quadratic, and if we find two numbers whose product is 3 and whose sum is 4, we have 1 and 3. So s plus 1 and s plus 3. So this will be h j omega is a over j omega plus 1 plus b over j omega plus 3. Now we need to find a and b. We need to find a and b. How we find a and b? Again, we combine here. We make crisscross. This is equal to a times j omega plus 3 plus b times j omega plus 1. And the denominator stays the same, j omega plus 1 times j omega plus 3, which is this one. Now we combine similar terms from this. We combine the j omega part. When we combine the j omega part, we have j omega a plus b. And we combine the constant part. The constant part is 3a plus b. This is equal to the numerator. What is the numerator? The numerator is j omega plus 2. So from this relation, what I have, in order the left side to be equal to the right side, okay, in the left side I have a plus b is the coefficient of j omega, and in the right side the coefficient of j omega is 1. So a plus b should be equal to 1. And in the left side I have the constant 3a plus b, and in the right side I have 2. So 3a plus b is equal to 2. So we have here two equations with two unknowns. What is this? This is called, as you know, simultaneous equation. We can solve it by substitution and variable elimination, or directly here if we make subtraction, minus the first equation minus the second equation. I have minus 2a is equal to minus 1, and a is half, and then b is 1 minus a, and b is also half. Now we found a and b. It is easy to change it to time domain. Okay, so if we change this to time domain, because remember e to the power of at ut, if a is greater than 0, the Fourier transform is 1 over j omega plus a. So 1 over j omega plus a. So using that relation, I can change it. Here, a is 1 here, a is 3, so this will be half is just constant. This will be half e to the power of t minus ut, and this one half e to the power of 3t times ut. So we solved the differential equation by going from time domain to frequency domain, and then from frequency domain to time domain. Now, let's have another example. Let x of t e to the power of at ut, a greater than 0, h of t e to the power of bt ut, b greater than 0, find y of t. So what is the step? What are the steps? Change x of t to x j omega, change h of t to h j omega. So x j omega is 1 over j omega plus a, h j omega 1 over j omega plus b, and I have here y j omega, x j omega times h j omega. Again, this is y j omega, and when we change it to time domain using inverse Fourier transform, it is easier to do partial fraction expansion. So we have here a over j omega plus a, capital A, plus b over j omega plus capital B over j omega plus b, and then again combine this crisscross a times j omega plus b, b plus j omega times a, and then I have here the numerator part, everything the numerator part, and where I combine them, a plus b times j omega, and I have this constant part. A plus b should be 0. Why? Because I don't have j omega in the numerator here. So should be 0. And this one, a capital A times small b plus capital B times small a should be 1. So we solve for a and b using the two equations for capital A and for capital B, and we have capital A and capital B given by this. So after that, we can change it to time domain again. This is e to the power of at ut, e to the power of bt ut. Okay, so this is the way to solve it using frequency domain and changing to time domain. Now, if I have, for example, a cascaded system, how we can be able to solve? Cascaded system means I have here input x of t. I have system, the first system, the output of the first system is wt, and it becomes an input to the second system, h2t, and I get yt. So the overall system is h of t. So what is yt? Yt x of t convolved h of t. And in frequency domain, y j omega is equal to x j omega times h j omega. So the overall system in time domain, h of t, is h1t convolved with h2t. Or yt here, the output yt is wt. Wt is x of t convolved with h1t. That means wj omega is equal to x j omega times h1 j omega. And what's yt? Yt is wt convolved with h2t, system 2. So from here, when I change it when I substitute for wt, what's wt? Wt is x of t convolved with h1t, and change it to time, y j omega is equal to x j omega times h1 j omega times h2 j omega, which means if I compare equation A is this, y j omega x j omega times h j omega, and equation C is y j omega is equal to x j omega times h1 j omega times h2 j omega. I have h j omega is h1 j omega times h2 j omega, the product of the two frequency response. Or in time domain, h of t is equal to h1 convolved with h2t. So this is the overall frequency response. The overall impulse response is h1t convolved with h2t. The overall frequency response is h1 j omega times h2 j omega. Now let's have this system, and the first system is described by differential equation. So W is the output, d by dt of Wt plus 2 times Wt is equal to x of t. So it's first order differential equation. And the second system is given by exponential function here, e to the power of minus 3t ut. Required, find the overall frequency response, h j omega. B, find h of t. That is, you change h j omega to h of t. So how to solve this? Okay, so from the first differential equation, we can get the frequency, the frequency response, h1 j omega, and from the second, we can get h2 j omega. So here I have change it to frequency domain, w j omega equals to x j omega times h1 j omega, then w j omega over x j omega is equal to h1 j omega, the first frequency response. And y of t is x of t convolved with h of t, the overall frequency response, the overall impulse response. So x of t convolved with h1t convolved with h2t. Therefore, y j omega is x j omega times h j omega, which is equal to x j omega times h1 j omega times h2 j omega. And we know h of j omega is h1 j omega times h2 j omega. So what is h1 j omega? Okay, so we change this to frequency. This first equation, the first order differential equation relating the output of the first system to the input. So I have j omega times w j omega plus 2 times w omega is equal to x j omega. What is common? Common is w j omega into j omega plus 2 equals x j omega. So w j omega over x j omega is equal to 1 over j omega plus 2, which is equal to h1 j omega. So this is the frequency response of the first system. So when I change it to time, it will be e to the power of minus 3t times ut, which is in frequency domain 1 over j omega plus 3. This is for the second for the second system. h2t is equal to e to the power of 3t ut, then h2 j omega 1 over j omega plus 3. So I found the frequency response of the first system, the frequency response of the second system. So the overall frequency response is h1 j omega times h2 j omega, which is 1 over j omega plus 2 plus j omega plus 3. So what is this in time domain? Again, we need to do partial fraction expansion. A over j omega plus 2, b over j omega plus 3. And we rearrange this. We have a plus b times j omega plus 3a plus 2b. This is a constant part. This is a coefficient of j omega. But in the numerator, I don't have j omega. So a plus b is equal to 0. And the constant part, 3a plus 2b, should be is equal to 1. So from here, from the first, b is equal to minus a. And substitute in the second equation, we have a1, b minus 1. And we have here the overall frequency response. And change it into time, e to the power of 2t ut, e to the power of 3t ut, and this will be the overall impulse response of the system. So this is how we solve differential equations. So in general, to summarize, we change the differential equation to frequency domain, and in frequency domain, we solve the required either the frequency response or y j omega or x j omega, and we change it to time domain. So please practice with the rest of the class exercise problems which are posted in Blackboard. And if you have any issues or any problems, you can always email me. and thank you for listening to this lecture.